So when we say classic polar curves, we're really using a phrase that is analogous in polynomials to parent graphs, which just means depending on the structure of the polar equation, we can predict the shape and many of the points in the polar graph, which is very, very convenient. So the first one we know already is a circle. These are what we worked on last time. And the equations for the circle are of the form r equals plus or minus a times the cosine of theta, and r equals plus or minus a times the sine of theta. And remember, these had symmetries about the polar axis and the line, the horizontal axis, pi over 2, theta equals pi over 2. So if we look at those, the cosine circle, logically, because we're talking about cosine, is centered over the right-hand side of the polar axis. And there was another cosine function that was centered over the left-hand side of the polar axis. In fact, the positive a will result in the right-hand side configuration, and the negative a will result in the circle on the left-hand side. So too with the sine function, only the sine circle is centered about or has symmetry with respect to the horizontal pi over 2 or 3 pi over 2. And the positive a will be on the positive side, or the upper above the polar axis, and the negative a is below. So negative a graphs here, positive a graphs here. A has some special information in it. The absolute value of a is the diameter of your circle. Same thing over here, absolute value of a is the diameter, which means that absolute value a over 2 is the radius. For each of these circles, I have a diameter of a and a radius, I'll put radius on this one, radius of a over 2. That's a lot of information, and it's so useful and so much information that I can do a lot of the circle sketching without having to use polar graph paper or even plotting points. If I want to graph, whoops, I'll put my grid up first. If I want to graph r equals negative 2 sine of theta, easy enough to do. Let's look at the information first. Well, sine of theta tells me that I'm going to be on the horizontal, to be centered over the horizontal line. 2 tells me I'm going to have a diameter of 2 or a radius of 1. And negative tells me that I'm going to be on the bottom or underneath. So that would be the negative. So if I want to graph this, I just have to put my circle in, and I can label my diameter is 2, or this point would be 2, and my radius is 1, or this point would be 1, and the axis of symmetry in this case would be theta equals 3 pi over 2. So that's enough to sketch the graph in. If I need to know an exact value to some point, then I would have to determine the angle for that point, plug it in for theta, and calculate r. So for any point other than those on the axis of symmetry, I have to calculate, but those on the axis of symmetry, I totally know where they are. So those are circles. Much easier to graph this way than the way we did last time, where we plotted all the points, even though plotting all the points had value in showing us that we got a circle. The next polar curve that we want to look at, or classic polar curve, are limacons. Limacon. And I think I said it wrong. Limacon. No, that's right. So limacon, it's French, it means snail. And they have general equations that look like r equals a plus or minus b cosine theta. Now there's also one for sine theta, but I'm going to start just with cosine theta. Now notice that this looks almost exactly the same as a cosine theta, or plus or minus a cosine theta, except I've added something to it. That's exactly what a limacon is. It's a circle that has a little play on it. So if I took a circle and folded it or twisted it so that it made an inner loop, I would get a limacon, and the loop is a result of, and the changes in the loop are the result of interactions between A and B in the equation. So let's do a rough sketch and talk about how much information we can find from the equation or get from the equation. So if I put in the loop, the rest of it sort of does this crisscross over. So the act of putting in the loop causes the circle to push onto the other side of the horizontal axis. So I have cosine, which means it's going to have its axis of symmetry horizontal at either the angle theta equals pi or on the polar axis. If it's a plus b cosine theta, it's to the right, just like up here. If it's a minus, it would have been to the left. So the outer part, we're not looking at A yet, we're just looking at plus or minus b cosine theta. So far, all of the behaviors that we saw in the circle are true for the limacon as well. The distance from the opposite axis to that of the axis of symmetry, so in this case, the distance from theta equals pi over 2, all the way to the intercept here, this distance, which coincides with the intercept with the polar axis, is equal to a plus b. Now be careful here because I'm talking about actual a plus actual b. Maybe I'll put absolute values around it. So I take whatever a is and I add whatever b is, disregarding these pluses and minuses. These mean something different. Also, a gives us our intercept values for the opposite axis. So this would be a and this would be a. And remember, it's not positive a and negative a because these values actually fall on the circles of a polar grid. The last comparison that we make and the last information we can get from the equation before we have to plot points, the dreaded plot points, is to compare the value of A and the value of B. Remember, the plus and minus sign we're not going to worry about. That just tells us that the limacon would flip to the other side, or if it's at the top for sine theta, it would flip down to be at the bottom. So the comparison between A and B, you have A could be less than B. That's one comparison. You have the comparison A is equal to B. You have the comparison that A is bigger than B, but still smaller than twice B. And then you have the comparison that A is greater than or equal to B. So you have 4 comparisons, each of which will indicate a variation to the shape, primarily in this area here. Okay, if A is less than B, then you get a traditional limacon. So if A is less than B, if I were to graph it, I would get a full inner loop and I would get the full outer loop, just like this. If A equals B, it has the effect pretty much, there will be some shifting of the outer loop, but the effect overall, or the specific effect, is that the inner loop disappears, which means that you're left only with this sort of heart-shaped outer loop. In fact, it gets its name from the fact that it looks sort of like a Valentine's heart. It's called a cardioid. It's still a limacon, but it's a cardioid variety. If B is littler than A, but A is still smaller than 2B, then you lose the point of a cardioid and you get just sort of a dimple and then the rest of it. And that, sorry, my other hand touched the pause button. This is called a dimpled limacon. Last but not least, if A is greater than or equal to 2B, this was a mistake, 2B, then the dimple just starts to flatten out and disappear, and you get something that sometimes can look like a full circle, but it never really is. You get that flat side on one side, and you get the rest of it. So it looks sort of like a circle where you just smashed in one side. And this is called a convex limacon. All right, so I think we're ready to graph. I know, we've put it off as long as we can. Trust me, it's way more fun than it seems. And this time I'm definitely going to need a plane, or excuse me, a polar grid. Let's keep as much information as I can. And I think we'll do a sine function. Okay, so we want to graph r equals 1 minus 2 sine theta. So let's start with all the information we have. We know that 2 plus 1 equals 3. Well, first let's figure out where we are on the whole thing. Let me label it. So I'm going to call this 1, 2, 3, and 4. And I have a sine theta, which means it's going to be symmetrical on the horizontal axis. Minus 2 sine theta means it's going to be below the polar axis. So it'll be down here at the bottom. So my loop is going to be somewhere here, and my outer loop is going to be like that. Obviously, that's not the actual graph. Then that's one piece of information. I also know 2 plus 1 equals 3. So I know that the extent, the farthest reaches of the shape are going to be on this line here. 1 plus 2 equals 3. Okay. I also know that A equals 1. So the loopy part out here is going to be here and here. So that's actually a lot of information, and I haven't even started yet. I can almost sort of see what it's going to be shaped like from here. But let's go ahead and figure out the rest of it. And by that I mean plot the points. So I'm definitely going to want to use a calculator for this, and I need a table. So I have my R value, which is going to come from, I always like to put R first, but I have my theta value, which is going to give me my R values. Even though I'm going to use a table, I want to, a calculator, I want to keep it on my table in case I have to go back and look at something else. So I have R. So I'm going to start by putting my function in. I make sure I'm in radians and that I'm a polar graph, and I have R of 1, so I know I'm dealing with polar equations, and I want to put my equation in. So this is 1 minus 2 sine, and I have to use theta. Enter and double check that I have exactly the right thing. I do. And if I graph it real quick, let's see what it looks like, just because I want to make sure I'm doing the right thing. Oh, so I'm definitely going to want to change my boundaries on my graph later, but you can see that I've definitely predicted that it's going to be in the right place. But I want to find values using the table. I'm going to go first to table set. I want to start with the angle 0, and then this time I'm not going to try to give it intervals like yesterday or last lesson I did 15 degrees for the interval. This time I want to do something different. I'm going to come down here, and instead of auto, I'm going to choose ask. Okay, and what that does is when I put the table in, enter. when I put in my table or I look at my table, I have a bunch of values. I'm going to clear these out. No, it doesn't really like me to do that. I forgot that. So I'm going to choose the theta that I want to look at. Okay, so in this case, I'm going to put in theta equals 0. And when I press enter, it's going to give me my value. So if theta equals 0, then 1 is my R value. The next thing I want to check is pi over 6. And the calculator will let me put in pi over 6, but it'll give me a decimal back out. So I'm going to choose pi divided by 6. Pi over 6, it gives me a decimal, is 0. So for the angle pi over 6, I have 0. Now I want to move forward. I'm going to skip pi over 4. I don't find it's a very important angle when I'm doing these. It's obviously an important angle, but it's not one that gives me much more information. So I'm going to go right to pi over 3. And that's negative 0.732. Move on up to pi over 2. Oh, I need to press enter, don't I? You know, watching somebody use a calculator, tedious. Negative 1. And let's go ahead and plot a few of these and see if I have half of my graph. Because once I have half of it, then I can use symmetry to give me the other half. And I don't want to do more poking at my calculator than I need to. So when the angle is 0, I have an output value of 1. And that's exactly what I expected, isn't it, from my A value. So when the angle is pi over 6, right here, my output value is 0. So for the angle pi over 6, I have a 0. And I sort of expected to get a 0, didn't I? When my angle is pi over 3, I can find it, pi over 3, then my output is negative 0.732. So remember, negative 0.732 for pi over 3 tells me to go to the other side. And so if this is 1, hang on. I tell you, it's a tough balance between getting this small enough that I can see everything on the screen, but big enough that I can see the darn numbering on the graph. So I was at pi over 3, which is the angle right here, pi over 3, but the output is negative. When the radius is negative, remember I have to go to the opposite side. So the opposite of pi over 3 is 4 pi over 3, and now I want to take it to 0.73, which is just less than 1 right there. So it looks like that's going to be on my inner loop. Next, pi over 2 gives me a negative 1. That works. Or negative 1. So for pi over 2, I would be at 1, but it says to go to negative 1. So that's going to be right there. So now I have this part of my loop, right? And I'm wanting to figure something out over here, which means I think I'm going to get these values when I start putting in these values over here. So I want to go to 2 pi over 3. 2 pi divided by 3 takes me to negative 7 point, wait a minute, 2 pi over 3 gives me negative 0.7321 for a radius. So for 2 pi over 3, I'm going to go to the negative 0.7321. Oh, that's the reflection there, right? That would be expected. I think what I'm going to get is this, and I'm going to have to do more plotting than I want to. But I can tell that it does this and then this. So I'm going to need to know something over here. Eventually, it's got to give it to me. I think it's going to happen over here because we're talking about sine, right? All students take calculus. but that's a negative. So I want to be down into one of these. So let's look at 4 pi over 3. Okay, let's see what happens when I enter 4 pi over 3. $2.7321. That totally works for 4 pi over 3. I get 2.7. I get just about here. And that is definitely enough for me to plot this side of my curve, which tells me that my hands are shaky. This side of my curve, which tells me exactly what's happening on this side. And there we go. Maybe not as pretty as some others. There we go. That makes it look a little better. So there we go. I've graphed it in. Most of the information came from my equation using my A's and B's and my comparisons, most of my information. And the rest of the information is figuring out just the number of plot points that I have to plot in order to find the rest of the graph. They all work this way. Go and practice.